Today we will discuss about application of Schrodinger wave equation to simple harmonic oscillator. Okay, in the previous video we discussed about application of Schrodinger wave equation to rigid rotator. In today's class we will apply it on simple harmonic oscillator. Okay, so simple harmonic oscillator is a rather a very simple model that we apply to describe vibration and the vibrational spectra of a diatomic molecule such as HCl. Okay, though this is an approximate model, it is not an accurate or a correct model. Still, it serves many purpose. Okay, for simple molecules such as HCl, we can accurately predict the vibrational spectra of simple diatomic molecules such as HCl. The correct model to describe the vibration of any diatomic molecule is anharmonic oscillator. Okay, but the application of Schrodinger wave equation to anharmonic oscillator is out of scope of our syllabus, so we will restrict ourselves to the simple harmonic oscillator model. Before studying the application of Schrodinger wave equation to this model, first let us understand what do we mean by simple harmonic motion and try to understand some basic physics related to simple harmonic motion. Okay, so what is simple harmonic motion, which in short we call as SHM, simple harmonic motion. Okay, can you give some examples for simple harmonic motion? The vibration of a tuning fork. You have all used a tuning fork in your physics laboratory in your PU class. Okay, the vibration of a tuning fork or a pendulum, simple pendulum, the oscillation of a simple pendulum, all are example for simple harmonic motion. So what is a simple harmonic motion? It has certain characteristics. It is a to and fro motion. It is a to and fro motion, and it is a periodic motion. Okay, it is a to and fro motion and it is a periodic motion. What do you mean by periodic motion? If the motion of the particle, okay, is periodic with respect to time, that is after certain time interval, if the if the particle is located at the same position again and again, such type of motion is called as periodic motion. So let us try to understand the simple harmonic motion by taking the example of a simple pendulum. Okay, so let us consider this as the roof. Okay, what I do is I connect a ball of known mass. Okay, I have a particle of known mass m, which is connected to a thread or which is connected to a spring or a string, a support. Okay, for the weight of the ball. Okay, now this is considered as the equilibrium position. Okay, this is called as the equilibrium position, and this center of the particle or the ball, that I will take it as origin, that is x is equal to 0. So this represents the equilibrium position. Equilibrium position. Why it is called equilibrium position is, if I do not disturb the state of this system, it will continue to remain in this state forever if I do not disturb. So that is why this is called as equilibrium position. Now what I will do is I will disturb this system. Okay, what I will do is I will take this ball gently to a certain distance. Okay, to a certain distance somewhere here. Okay, I will take the ball somewhere here. Okay, say at this point the position of the ball is x is equal to a. It means I have taken the particle or the ball x a distance away from the equilibrium position. Okay, and what I will do here is, okay, of course you have also have the thread, okay, moving along with the particle. What I will do is I will gently leave the particle. I will gently leave it. I will not throw it. Okay, there is no certain thrust on the ball. What I will do is I will gently leave it here. When I leave the particle, okay, it will always prefer to go back to its equilibrium position. Okay, so the particle will move towards its equilibrium position, which is x is equal to 0. But when the particle comes to equilibrium position, it immediately cannot come to rest, because when the particle comes back to x is equal to 0, the particle is carrying certain momentum, and because the particle is carrying certain momentum, it immediately cannot come to rest. That is, it cannot immediately stay at its equilibrium position. What happens is that momentum takes the particle in the opposite direction from the point of equilibrium. So the particle will start moving in the opposite direction. And how far does it move? How far does it move? It moves an equal distance in the opposite direction. So I had taken the particle up to x is equal to a to the right hand side. It means the particle will be displayed to the same distance. It will be displaced to the same distance even to the left side. Okay. So the particle can move only up to x is equal to minus a. Okay. So this position is x is equal to minus a. So the magnitude of displacement is same, a units in both the direction. Okay. So the particle is now in the opposite direction from the equilibrium. Once the particle reaches here, it cannot further move ahead. Okay. And what happens is, once the particle reaches this maximum displacement, again it tries to come back to its equilibrium position. So it will again start moving towards equilibrium position. As I already told you, when the particle reaches the equilibrium position, it has a certain momentum carrying with it, and what does this momentum do is, that momentum again carries the particle in the right direction, and therefore again the particle moves up to x is equal to a. That is the largest displacement the particle can have. Okay. And it will again come back to tries to come back to its equilibrium, where it unfortunately cannot stop, and it again continues this motion from equilibrium to right, right to equilibrium to left, left to equilibrium to right, and this motion continues again and again, and that is why this is called as to and fro motion. And this is periodic motion. Why? Because if I leave the particle from here and start a stop clock, okay, a stopwatch, and I am measuring the time taken for the particle to complete one cycle of motion. So what is one cycle of motion? So the particle has started from here. When I started the stop clock, that is stop clock is showing t is equal to 0. The particle moves towards equilibrium position. It moves a equal distance in the opposite direction. Okay, it reaches the maximum displacement in the opposite direction. It again comes to equilibrium, and it again moves in the opposite direction, that is towards the right, and again it reaches x is equal to a. It means it has now reached its original position from where it has started this motion, and this completes one cycle. It means the particle has come back to its original position. So when the particle comes back to its original position, I will immediately stop the clock and record the time. Say for example t is equal to 7.8 second. This time is called as period. Okay, it is called as time period or period. It is the time taken for completion of one cycle of motion. Okay, so such type of motion is periodic in nature, because after every 7.8 second, which is the period of motion, after every 7.8 second, if I try to locate the position of the particle, it will always be observed at the same position. Okay, so this type of motion is characterized by a time period, okay, t. Similarly, this type of motion is characterized by another quantity which we call as frequency. Okay, I will use the symbol nu to represent frequency. So what is the frequency of a simple harmonic motion? Frequency is the number of cycles the particle completes in 1 second. Okay, so frequency is nothing but the number of times the particle executes simple harmonic motion in 1 second. For example, if frequency is 10 to the power 4 or 10,000, what does it mean? It means the particle has executed simple harmonic motion, that is, it has completed 10,000 cycles of such motion in 1 second. That is the definition of frequency. In general, the frequency is related to the time period by this relation. Frequency is inversely proportional to time period. Okay. Another important characteristic of the simple harmonic motion is the amplitude. Okay. So the maximum amplitude I have represented as x is equal to a. In general, the amplitude is represented by the symbol x. Suppose if the particle is somewhere here, it means the particle is displaced from its equilibrium position and it's somewhere here where the position of the particle is x. So this x represents the displacement of the particle from the equilibrium position, and a is the maximum value of displacement. So a is the maximum value of x. So here the maximum displacement is a, which is nothing but the amplitude. Okay. So amplitude is nothing but the maximum displacement of the particle from the equilibrium position. So a simple harmonic motion is characterized by three important quantities. Okay, one is the period or the time period, the second is the frequency, that is the number of cycles per second, and the third is the amplitude, which is the maximum displacement of the particle from the equilibrium position. Now let us try to understand some physics of the simple harmonic motion. So what I will do is I will parallelly take one more example for simple harmonic motion. Okay, and by taking both the examples together, let us try to understand some basic physics of simple harmonic motion. Okay, so what I will do is I will take a particle which is lying uh, an object, okay, which is lying on the floor. So this is the floor, which I will take it as x-axis. Okay, so this is the y-axis, which is the wall, and the net force acting on this object is equal to 0. So what we will do is we will connect this object by a spring. Okay, we'll connect this object by a spring, and you know the characteristic of a spring, it can be compressed or it can be elongated or stretched. So now this represents the equilibrium position. It means the string is in its natural length. Okay, the string is neither compressed, neither it is elongated, it is in its natural length. It is in its equilibrium state. Okay, so the particle's position, okay, if I take the center of the object as the reference point, so the position of the object, okay, I will take it as x is equal to 0, and again this represents the equilibrium position. So let us assume that this is a frictionless floor. Okay, there is no friction acting. Now what I will do is I will take this object to the right. I will take this object to the right gently. Okay, so when I am taking the object to the right, it means I am stretching the string. Okay, stretching the string, and we know that the string cannot be stretched infinitely. Okay, at a certain point, after the string is stretched to a certain extent, if I try to further stretch the string might break. Okay, so there is a limiting point up to which this string can be elongated or stretched. Okay, so I am taking this particle to that limiting situation. Say for example, I can stretch the string such a way that the particle can be moved up to this particular point. So this is the maximum displacement the particle uh, can be displaced from the equilibrium position. So this position actually now represents the maximum displacement of the object from the equilibrium position. So I take it as x is equal to a. So At this particular stage, the string or the spring is elongated as maximum as it could be. Okay, so if I gently leave the object, it will not remain there because the spring is not in its natural state. Okay, this is the natural length of the string, or this is the natural state of the spring or the string. So when the object is kept here, the string is elongated, which is not its natural state. So what this spring will do is it will try to apply a force on the object and tries to bring back that object to the equilibrium position. So there is some kind of force when I am taking the object away from the equilibrium position. There is some kind of force acting in the opposite direction, which is trying to restore the object to its equilibrium position. So if the object is displaced towards the right, which I have done here, then there is certain force that is acting through the spring, which is trying to bring back the object again to the equilibrium position, and this force is called as restoring force. Okay, why it is called as a restoring force? Because it is trying to restore the equilibrium condition. It is trying to bring back the object to the equilibrium position so that the spring would remain in its natural length or natural state. So when the object is displaced to the right, there is a force acting to the left. So I have displaced the object as maximum as possible. This is the limiting point. Now what I will do is I will leave the object, and when I leave the object, as I already told you, there is a force, maximum force acting in the opposite direction, and this force tries to bring back the object to equilibrium position. But what happens when the object comes to equilibrium position is it will not stop immediately. It will not come to rest immediately at the equilibrium position because there is some momentum that is carried by the object, okay, or the particle. So what happens is, instead of coming to rest, the object will move in the opposite direction from the equilibrium position. How much it will be displaced in the opposite direction? As I already told you, it will be displaced in the opposite direction. It will be equally displaced in the opposite direction. So the particle will be displaced somewhere up to here. Okay. So this is x is equal to minus a, or it is x is equal to a in the opposite direction from the equilibrium position. So now what has happened is, this when the object is here, the spring is not in the elongated or the stretched state, it is now in a compressed state. So this string or the spring is compressed, and this is also not a natural state of the spring. So what the spring will do, it is compressed to the maximum extent. So because it wants to come back to its equilibrium state or the natural state, it will try to push the object in the opposite direction again towards equilibrium. So when the object is moving in this direction, so this is the direction of displacement towards left, there is a force acting towards right. Okay, so whether the object is in the stretched mode or whether it is in the compressed mode, there is always a force acting in the direction opposite to the movement of the object. If the object is moving towards right, there is a force trying to pull it back towards the equilibrium position. If the object is moving towards left, there is a force acting in the opposite direction which is trying to take back the object to the equilibrium position. Okay, and if the floor is frictionless, that is the object does not lose any energy due to friction, this motion will continue for infinite amount of time. Okay, so this will continue for infinite amount of time. The object will be displaced toward the right to maximum extent. Okay, then the spring will try to bring back the object to equilibrium position, but the object cannot come to rest, certainly to rest at equilibrium position. So the object will move in the opposite direction when the spring is compressed. So the spring will try to push that object again in the opposite direction. So this to and fro motion or the simple harmonic motion will continue. for infinite amount of time. So both are example for simple harmonic motion. And what we have observed here is a very important relation between the force acting on the object through the spring and the displacement of the object. What we have observed is the force acting on the object, which is called as the restoring force, is directly proportional to the displacement of the object. Okay, when the object is at the equilibrium position, that is when x is equal to 0, there is no force acting on the object because the spring is in its natural state. But when I start moving the object from the equilibrium position, say for example towards right, it means as the value of x increases, the force acting on the object increases, and when this point is reached, maximum force acts on the object, and therefore the object cannot be further uh, displaced because there is a maximum force acting on the object. If I try to take the object further beyond that point, what may happen that the spring may not tolerate such amount of stretching and spring may break down. Okay, so this is the maximum displacement. So a maximum force acts on the object. So when the particle reaches this position, there is a maximum force uh, trying to pull the object backwards. So because of that maximum force, the particle again comes to this position, x is equal to 0, and when the particle is moving the opposite direction, and when the particle reaches here, again here a maximum force is acting on the object. And what is that maximum force trying to do? That maximum force is trying to push the object back to the equilibrium position. So at any instant of time, the force acting on the object is directly proportional to displacement from the equilibrium position. Greater the displacement from the equilibrium position, greater is the force. And where does the maximum force lie? The maximum force is at these two extreme situations. So here also, when there is maximum displacement, which refers to the amplitude, here the force is maximum, whereas here the force is 0 because the particle is in the equilibrium position. And to emphasize that the force and displacement are in opposite direction, you know that force and displacement are vector quantities, and since in both the cases they are in opposite direction, we write force is directly proportional to minus x, or we write force, the restoring force, is equal to minus k into x. So the motion of particles which obey this mathematical condition, okay, such motions are called as simple harmonic motion. And this condition, which is known as a law, okay, this law is called as Hooke's law. So what is a simple harmonic motion? Any motion, periodic motion, will be called a simple harmonic motion if it obeys Hooke's law, which is force. The restoring force is directly proportional to minus x, or force is equal to minus k into x, where this k is called as force constant, okay, which represents the strength of this spring. Okay, it represents the strength of the spring up to which it can be compressed or elongated. So it represents the strength of the spring. Okay, now let us comment on certain other physical aspects, physics aspect of simple harmonic motion. Okay, we know that the potential energy V of such type of simple harmonic motion is given by V is equal to half into k into x square. Okay, so force is given by minus k into x. Okay, because the force is given by this equation, because of certain equations in physics, it can be shown that potential energy for this force should be equal to half into k into x square. So the potential energy of simple harmonic motion is given by V is equal to half into k into x square. So what we see here is potential energy depends on the position of the particle. Okay, k is again the force constant. So let us try to understand the potential energy of the object at a different position. When the object is at equilibrium, that is there is no displacement, x is equal to 0. When x is equal to 0, V becomes equal to 0. So when the particle is in the equilibrium position, no force is acting on the particle, and therefore its potential energy is 0. What does it mean? All the energy is in the form of kinetic energy. So when the particle is in the equilibrium position, all the energy is stored in the form of kinetic energy. And let us consider this extreme case when the particle is at x is equal to a or x is equal to minus a, which is the maximum value of x, that is the maximum displacement. So when at x is equal to a or minus a, the potential energy is maximum and it is half k into a square. So this is the maximum potential energy the particle can achieve. It is when at the maximum displacement at x is equal to a or x is equal to minus a. So what does it mean is when the particle is in the extreme positions, that is at x is equal to a or minus a, that is when it is extremely stretched or compressed, here the potential energy is maximum. So here all the energy is in the form of potential energy. Okay, so when the particle is in the equilibrium position, all the energy is of the system is in the form of kinetic energy. When the particle is at the uh, extreme positions, all the energy is in the form of the potential energy. So here potential energy is zero because all energy is in the form of kinetic energy. At these two extreme positions, kinetic energy is zero because all the energy is in the form of potential energy. Suppose if I consider certain intermediate position here, then here the kinetic and the energy of the particle is sum of kinetic energy plus potential energy. Okay, you know that the energy is always conserved. So whether the particle is at the equilibrium or it at some intermediate position or whether it is at the extreme position, total energy remains always same. But our total energy ಯಾವ ತರ ಇರ್ತದೆ, what is the nature of the total energy, it depends on the position of the particle. If the particle is at the equilibrium position, kinetic energy will be maximum and all the energy is in the form of kinetic energy. Here all the energy is in the form of potential energy. Here potential energy is maximum and all the energy is in the form of potential energy. At some intermediate position, the some part of the energy is in the form of kinetic energy and some part of the energy is in the form of potential energy. So neither kinetic energy is maximum here, neither potential energy is maximum. So the total energy is sum of kinetic energy and potential energy. So when the particle is here and I take the particle to the one extreme position, so here maximum force is acting on the particle according to Hooke's law. It means potential energy is maximum, all the energy is in the form of potential energy. If I gently leave the particle here, because of the restoring force, the particle will try to come back to its equilibrium position. So what happens to the energy when it comes back to equilibrium position? Here all the energy was in the form of potential energy. When this particle or the object starts moving towards equilibrium position, what happens is some potential energy will be converted to kinetic energy. So here at the intermediate position, the total energy contains both kinetic and potential energy. So when the particle comes closer and closer to the equilibrium position, what happens is the potential energy will be converted to kinetic energy, and when the particle reaches the equilibrium position, all the potential energy will be converted to its kinetic energy. So here kinetic energy is maximum. What does it mean? When the kinetic energy is maximum, the momentum is also maximum. So here the momentum of the particle is maximum because force is zero according to that equation. So because of that high momentum or large momentum, the particle is not at rest. It has to keep on its motion in the opposite direction. When the particle starts moving in the opposite direction, again a force starts acting on the particle towards the equilibrium position. So as a result, what happens? All the energy was in the form of kinetic energy here, and the particle starts moving in the opposite direction. The kinetic energy again gets converted partially to potential energy, and when the particle reaches the extreme position, all the kinetic energy would have been converted to potential energy. So again this motion continues to and fro. So here the potential energy is maximum, here the kinetic energy is maximum, all the energy is in the form of kinetic energy, and at all other intermediate position, total energy consists of both kinetic energy as well as potential energy. Okay, this is some simple physics about simple harmonic motion. Now let us try to explain how this type of simple harmonic motion, this is a simple harmonic oscillator model, how this type of model can be used to explain the vibration of a diatomic molecule, how this vibration of or the oscillation of a particle is equivalent to vibration of a diatomic molecule such as HCl, how they are equivalent to each other. Okay, so let us try to understand the analogy or similarity between these two models. Then you will appreciate how the vibration of a molecule such as HCl can be treated by using this model. Okay. So if I take HCl molecule, okay, it is a uh, heteronuclear diatomic molecule. What do you mean by heteronuclear diatomic molecule? It is made up of two different types of atoms or different types of nucleus. So hydrogen, okay, you know, is the lightest element in the periodic table, and compared to chlorine, okay, the atomic weight of hydrogen is very less, or in other words, chlorine is very heavy compared to hydrogen. So what we assume that when this HCl molecule is vibrating, because of this heavy chlorine atom, we assume that the position of chlorine atom is fixed, and it is only the hydrogen atom that is exhibiting to and fro motion. Strictly speaking, chlorine is also exhibiting certain motion, but since it's very heavy compared to hydrogen, we approximate that and assume that its position is almost fixed, and it is only the hydrogen atom that is vibrating, that is, it is exhibiting to and fro motion. So let us try to explain the vibration of HCl along and compare it with this model. So let me keep chlorine here. So this is chlorine atom. So the wall in this model is replaced by chlorine atom. This wall is fixed. Similarly, the position of the chlorine is fixed, assuming that its position is fixed because it is very heavy. Okay, and the spring in this model is replaced by a bond, a chemical bond between hydrogen and chlorine. Okay, and this particle here, okay, the particle here, it is replaced by a small hydrogen atom. Okay, it is replaced by small hydrogen atom. Chlorine analogy is wall, hydrogen analogy is this particle, and spring here, it is nothing but a bond. Okay, a covalent chemical bond between hydrogen and chlorine. So we assume that the position of chlorine is fixed. So this is the position equilibrium position, and this hydrogen atom is exhibiting to and fro motion. This hydrogen atom, if it moves in the opposite direction, okay, some up to somewhere here, say for example x is equal to a, so this is the stretched, okay, position. The hydrogen atom cannot move further. Why? Because if the hydrogen atom moves further, it moves away from the influence of chlorine atom, so then there is a possibility that this bond may be broken. So this is the maximum limit to which this bond can be stretched. Okay, just like how the spring can be stretched to only to certain extent, so this is the maximum extent to which the bond can be stretched. And once the hydrogen atom comes here, because of the force exerted by the chlorine atom, force of attraction, which is a restoring force type of force, so this hydrogen atom comes back to its equilibrium position, but it cannot stop there because of the momentum, and it will move in the opposite direction. It will move somewhere up to here, equal direction in opposite direction. So this position is x is equal to minus a. So this represents the stretched mode, and this represents the compressed mode. The particle cannot further move ahead. Okay, why? Because after this point, the force of repulsion between the electrons at the nucleus of hydrogen and chlorine atom becomes far more dominating than the force of attraction between these two atoms. So because of that force of repulsion, This is the limit up to which the HCl bond can be compressed. So once the hydrogen atom reaches here, this position x is equal to minus a, again the restoring force, that is here the force of repulsion, okay, takes again tries to take the hydrogen atom to its equilibrium position, and this to and fro motion will continue. So the vibration of a HCl molecule is similar to the uh, simple harmonic oscillator model. The only thing is here the wall is equivalent to the fixed chlorine atom, and this object is similar to the hydrogen atom, and the spring is in this problem is replaced by a chemical bond between hydrogen and chlorine. So the vibration of a molecule such as HCl is similar to the simple harmonic oscillator. So we are using this model to describe the vibration and the corresponding vibrational spectra of HCl molecule or any other heteronuclear diatomic molecule. As I already told you, this is not the correct realistic model. This is not the perfect model. It is actually the enharmonic oscillator model which explains the reality of vibration in molecules such as HCl, but that is out of scope of our syllabus, so we will only stick on to the simple harmonic oscillator model. So this is about some simple physics about simple harmonic motion. In the next video we will apply the Schrodinger wave equation to this motion, which is a simple harmonic oscillator model.